Alright guys, we should be back. How are you guys today? It's a new day. It is the third day in a row. Actually no, because it's my third Tryhackme day. And we've been doing really good. We've been completing the modules. And this lighting makes my teeth look kinda yellow. But let me check, of course, daily routine. Let me check if I'm streaming real quick. I was watching a video, let's add that to watch later. Because we need to lock in. So let me see if we're streaming. Let's see. Alright, so everything should be good. We're up and streaming, so let's get right onto it. So today we are completing the computer fundamentals. So after this we have the operating system basics, software basics, and attacks and defenses. So I'm excited for this one, become a hacker. So let's see. This is all building up to that. So let's start, guys. Let's start this module 4, computer fundamentals. Alright, let's start this right now. Alright guys, we're good. So wait, do we have the oh, we still do have the keybind. Okay. Alright, so join the room. Okay, so welcome to the first of the computer fundamentals module. Before we can talk about security, we need to understand what we're securing. Because I want to make sure you guys are can see it well. Okay, so before we can talk about security, we need to first understand what we're securing, obviously. So considering the following analogy, before protecting a castle, we need to know the layout of the castle, where the treasure room, the food storage, and the commander's quarters are. We need to know who enters and how to enter the castle. Also important is who can enter these rooms and to take or put pressure food, for example. The bottom line is, trying to defend what you don't understand is like defending a castle you have never seen. In this room, we will explore our castle, where we'll cover what a computer is, its building blocks, and how they are connected. After completing this room, you will have a general idea of how the components of a computer system interact with each other to provide services to its users. Don't worry about too much technical jargon or depth. We'll take this nice and easy and focus on the fundamentals. This is what I love about Tryhackme, that they never pressure you to do anything, that it makes it like a safe zone. Okay, sorry, I'm a really curious guy. Okay, learning objectives. After completing this room, you will be able to recognize and understand the functions of various computing components. Alright, so prerequisites. Motivated to step into the digital world of computing, which I really am, and I hope you guys are too. So you guys can join me on that. Let's check. No answer needed. Alright, so inside a computer system. Okay. Nearly every computer system that you can think of includes, in one way or another, the same building blocks. Each part has its own job, and together they make the computer work. Let's have a look at each of these building blocks. Alright. So throughout this task, we will use a very relatable analogy: the human body. The image above shows the different PC components and its human counterpart. To learn about each component, open the static site by clicking on the green View Site button below. The static site should open in split screen view. So motherboard, the skeleton and nerves. Okay. The RAM, short-term memory. The PSU is the heart and lungs. So I'm just looking at my PC right now, and I'm seeing all these things because I have a see-through PC. So CPU is the brains. Okay. GPU is the visual cortex, which like your eyes or something. I don't freaking know. Oh, I think that's like how the quality and stuff. The long-term memory. Okay. Is the HDD and SSD. Click a component to discover what it does. Motherboard. We said that was like the skeletons, right? Yeah. Let's go. motherboard. Okay, the motherboard is like our body, skeleton, and nervous system. It holds all the different components in place and connects them. On a typical desktop motherboard, you'll see different connectors that house all your components: CPU socket, RAM slots, expansion slots, and various ports. Every other component plugs into our or connects through the motherboard. And the image below shows a typical desktop motherboard. Okay, so I can tell like how like each thing fits on the motherboard. Okay, so CPU. So CPU, I think that's the no, yeah, I did think it was the brain. So yeah, the brain. So am I okay? So I was thinking of like the brain as being like storing to the memory, but that's RAM. I mean, I thought the brain was gonna be like that's crazy. I was thinking of it like the wrong way. So the brain is like the thinking, of course. All right, RAM. So how would you describe temporarily? Yeah. So it's like short-term memory, fast but temporary. It's compared to our brain's short-term working memory. When working on a task, we keep relevant information in mind temporarily. RAM does the same. It holds data that the CPU needs quick access to. RAM is volatile. When power is lost, all contents are gone. Modern RAM modules use technologies like DDR5 or DDR6 for increased speed and performance. The image below shows a RAM module for a desktop. So here it is. Storage. So that's a long term, right? Yeah, there we go. All right, so I think we all know what SSDs. They're just like storage devices, network adapter. Which one's that one? That's just the like networks. Yeah. Okay, so just like we use our vocal cords to communicate, okay, I like this analogy. A network adapter lets computers communicate with other systems. Network adapters come in wireless and wired variants. Often they are embedded in the motherboard, but they can also be added as expansion cards. Network cards typically connect via PCI Express ports. The image below shows a plug-in network card typically used in desktops. So I believe this is the right here. So I think this is a Ethernet port right there. So I can see why that is the network. The power supply, yeah, like the heart pumping everything. Okay, so that's what it is. Okay, graphics, of course, is the graphics. That's the graphics card. Input and output, obviously that's to no, that's to there we go. So let's read this one because that was a little tricky. Just like we have senses to obtain information for our brains to process and then act on, computers have input and output devices. Input devices include keyboards, microphones, mice, and scanners. Output devices include monitors, printers, and speakers. Common connectors for those peripherals include USB, HDMI, and DisplayPort. The image below shows a few of the basic I/O devices. So input is like the keyboard, this and that, and the output are these. So that's like the monitors, and all that. So okay. So inspection. So let's see. Okay. So here's a little exercise. Okay. So let's start this exercise. CPU. CPU. RAM. Okay. No. Let's go to input output. The SSD card. What the frick is that? Oh, that's a network adapter. I just want to see like what I can like put it. Okay, so these that should be the S. What's that? Is that RAM? Yeah. Graphics. Those are network adapters too. No, hold on. The network adapter. Because I feel like I'm getting this wrong. I feel like this is the power supply. What else am I missing? Alright, so I'm just missing those two. Oh, why can't I replace like both of them? Graphics card. I'm just gonna like just to check. So that's obviously input output. It's obviously not the power supply. Guys, don't judge, don't judge. Chill, chill, chill. So I know this PSU is supposed to be like yeah, the box. Like it looks like a box. Like I have a PSU right there that looks like a freaking box. I'm just gonna guess, guys. I'm actually having trouble. So what is that, bro? Okay, let's review. Oh, okay, I actually did not know. Hold on, sorry guys. Okay, input output. This CPU, graphics card, graphics. So these are all graphics card. That's the storage. That's the PSU. Okay. Okay, so okay, we should be good. So this one's CPU, storage, graphics card, graphics card. Input output, obviously. And power supply. RAM. Dang it, bro. What am I getting wrong? Let's go back to the inspection. Network, graphics, CPU, RAM. I'm just thinking like big, like the power supply is big, but network, graphics, storage, and then input output. Let's go. Wait, why am I not receiving the sound effects from it? Oh, okay, there we go. Alright, so That took a little bit, but I needed that, and we all need that to start out. You know, I'm gonna see my stream real quick, guys. And actually, let me fix my stream real quick. Let me just fix this, guys. Give me 1 sec. Alright, so it should be good now. Okay, so let's get back into it. Okay, so now that the core components are installed in the computer system and it's time to boot up the system, we can compare this to how we wake up in the morning and do a quick check to see if everything is working. Only when everything is okay do we get up and start our day. The image below shows the steps a computer system goes through before it shows you working interface in the form of an operating system. Press power button, firmware starts, post, select boot device, and then start bootloader. Okay, so press the power button. When you press the power button on our system, a signal is sent to the PSU to allow power to flow. Imagine our body being powered off when we sleep. Once we wake up to receive oxygen, our body starts pumping blood and boots up. Firmware starts. Continuing our analogy from step 1, once the body has started up, our core components are up and running, but our brain is not yet conscious. Like our bodies, a computer system contains firmware that allows all of its components to start up. The central system that manages this is called a Unified Extensible Firmware Interface. Note, we will often see the term BIOS mentioned instead of UEFI. BIOS does the same as UEFI, but has mainly been replaced by UEFI. Okay, power on self-test. Now that our body's up and running, it is time to test if everything is functioning as it should. If something isn't, then there will be some alarm signals. One of the routines that the UEFI loads is the power on self-test, which tests if every required component is present, configured correctly, and functioning. Select boot device. Once our body is up and running, configured correctly, and fully functional, our system searches for the location of our boot up routine to start a consciousness. In our computer system, the UEFI holds an order list which prioritizes on which devices to look first for the boot up routine for operating system. Initiate bootloader. Now that our system knows the part of our brain where our consciousness is located, it initiates the load routine to start it. Our computer system follows a similar process on the selected boot device. The bootloader is initiated. This bootloader transfers the operating system from the selected boot device to the random access memory, which is the RAM. Once the OS is transferred, the UEFI gives control over the different components to the OS. Now that we know how a computer boots, let's have a little exercise. Open the static site. Alright, let's press the power button. So, let's go. And then UEFI, initializing card is the first software that runs. So, let's go. Okay, the post test, power on self test. So, let's see if it's working. So boot device, UEFI follows a priority to determine which device to boot from. Typically, oh shoot, it follows a configured boot priority list. Okay, so it has like a routine. Boolean lowest operators. All right. So then we have the press. All right. Okay, let's go. We have covered the core components of a computer system and how it boots up. At the moment, you won't realize this, but further on, when learning cybersecurity concepts, you will often need to recall the function of each of these core components and how they interact with each other. The boot process is a very important concept later on, as it is sometimes targeted by hackers. Now that we know that the insides of a computer, the next step is to see how the different combinations and specializations of these components lead to diverse types of computer systems. Continue to the next room to find out. Let's freaking go, guys. Okay, that was probably annoying for you guys. That was probably really annoying for you guys. Alright, so this one is about explain the different types of computers from laptops to the tiny chips inside your coffee machine. Okay. Alright, so Sophia was trying to connect a new device to her home's Wi-Fi when she noticed something unexpected. The Nextcool Fridge X17. She laughed and wondered if connecting to the fridge Wi-Fi will let her download a cold meal. Setting the joke aside, I was like confused, and then I said, "Oh, setting the joke aside, okay, so that's a joke." All right, setting the joke aside, she soon realized her neighbor had bought a smart refrigerator, a fridge with a built-in computer capable of connecting to the internet. It made her pause. Computers were no longer just laptops and phones; they were quietly infiltrating everyday objects, from kitchen appliances to doorbells. Sophia had seen strange stories online about how smart devices behaving badly about smart devices behaving badly, but she had never really stopped to think about what these machines actually were. She looked forward to learning more about computers during her upcoming summer internship. Learning objectives. Upon completion of this room, you will be able to identify and distinguish between different types of computers used directly, such as laptops and smartphones, and indirectly, such as servers, IoT devices, and embedded systems. You'll also understand what makes each type suited to its purpose. So these are the different types of computers, okay. Alright, so the computers she's in front of. During her first month at Nova Labs, Sophia learned an important lesson. Sophia learned that not all computers are meant to move. Not all computers are meant for people to sit in front of. She was introduced to 4 types of computers that often look similar but serve very different purposes. Alright, portable everyday computing, sustained performance at a fixed location. Let's compare these below. Computer type, laptop, desktop, workstation, server. Screen and keyboard, yes, no. Main purpose, portable everyday computing, sustained performance at a fixed location, precision and reliability for professional tasks, and providing services to many users over a network. Okay. So, how Sophia learned the difference? Sophia began with a laptop, the computer she already knew best. It was perfect for emails and documents, but when she pushed it with long tasks, it slowed down. Gabriel explained. Let me fix something, guys, real quick. Sorry, guys. Okay, so Gabriel explained that laptops are built to be portable, and staying cool in a small, battery-powered device is difficult. Next, she tried a desktop. It stayed in one place, used all watt power, and had better cooling. The same task ran smoothly for much longer. Desktops are designed for consistency rather than mobility. When Sophia moved on to professional work, such as simulations and 3D models, Gabriel showed her a workstation. It looked like a desktop, but it was built differently. Workstations prioritize accuracy and reliability, using specialized components to reduce errors during long or complex computations. And then finally, Gabriel took her to a room full of machines with no screens at all. These were servers. They ran continuously, answering requests from multiple users simultaneously. Sophia never touched them directly, but they powered the tools she used every day. Which computer size usually runs without a dedicated screen and keyboard? So that's a server. What kind of computer with specialized components would one buy to carry out precision work? No, that's a freaking I spelled it out like PlayStation, you know. Um, by her second month at Nova Labs, Sophia had started noticing computers she had never interacted with directly. The most powerful computer most people own fits in their pocket, but millions more hide inside everyday objects, doors, lamps, and coffee machines. We continue to find computers hiding in everyday objects. So the types: smartphone, tablet, IoT device, embedded computer. What it is: smartphone is a pocket-sized computer optimized for battery life and connectivity. Examples: iPhone or Android phone. Tablet, touch-first computer with larger screen. iPad, drawing tablet. IoT device is a network-connected device with a singular purpose. So that's like a thermostat, smart doorbell, or a fitness tracker. Embedded computer, computer built into another device, copy maker controller, automatic door sensor, lamp dimmer chip. IoT versus embedded. Both can be small and single purpose. The device connectivity, the difference is connectivity. IoT devices connect to a network to report data or receive commands. Embedded computers might not connect to anything. They do their job inside of the machine, often for years without anyone knowing they exist. Sophia walked through automatic doors every day at Nova Labs. She never realized that a tiny computer inside the door frame was detecting her movement and signaling the motor to open. That's embedded computing. Invisible, reliable, everywhere. What is the most popular pocket-sized computer? A smartphone. What kind of computer would you expect embedded? Okay, so why do computers come in different flavors, you might ask? Well, Sophia asked a question that had been bothering her all summer. Why not just build a one computer that does everything? Because every design is a trade-off, replied Gabriel. Mobility costs power. Smaller portable computers must sacrifice sustained performance. Reliability costs money. Servers and critical systems use redundancy, such as extra power supplies disks to avoid failure. And purpose shapes everything. You touch your phone, you ask a server for information. An IoT device works quietly without demanding attention. There is no best computer. There's only the right tool for the job. Alright, so let's click the site. I'm really liking these. Sophia's first day. For hidden computers. Click items to check for hidden computers. We're supposed to. Okay, so let's see. Smartwatch. Smart TV. Smart. Okay. So it's this one. Oh, okay. I was supposed to answer. I thought I was supposed to answer a question. What keeps these servers running? Redundant power reduces singular uptime improves. Alright, match each job to the right tool. What is throttle more than desktops? What's throttle? Okay. What does server redundancy prevent? Why do smartphones last longer on battery than laptops? How many workstations? What coordinates devices? Let's go, dude. Let's go, dude. I mastered the fundamentals of computer types. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's go. I do not know what I just did. Alright, so here's final report began. I arrived thinking computers had a screen and keyboards. I leave knowing they are everywhere, especially where I did not see them. This room we covered 8 types and learned how. Okay, most critical computers. Okay, we got that. Let's go. So where's the screen? Okay, I was like, it's like waiting on the screen. So I'm in a league. That's pretty cool. What is my name, guys? Is my name still? No, guys, I want it to be Bean. Yeah, that one. My name is. Okay, so. Alright, so that should fix. Well, let's refresh because this thing has been bothering me. Hold on. Let's go, BC1. I just love seeing that, guys. There's a long story behind that name. Alright, so client server basics. Alright, so this one, client server basics. Okay, so in the previous rooms, we looked at different types of computers and how computers are used at work. Initially, most computers worked alone. They stored their own files, ran their own programs, and did not communicate with other computers. Soon, multiple organizations around the world started with the idea of interconnecting these systems to facilitate information exchange and resource sharing regardless of distance. Hence, the precursors of the Internet were born. Networks such as ARPANET, Cyclades, NPO, and NSFNet paved the way for the modern Internet. Just like in society where people distinguish themselves with a particular set of skills and offer these as service, interconnected systems are started to specialize as well. So how does this work? How are computer systems able to use services on another computer system? At the end of this room, you will know the answer to this question. Learning objectives: understand the CSM. Understand the following concepts on a service level: DNS, client, server, port, protocol, and network. Prerequisites coming soon. Inside a computer system, types of computer systems. So we did that. Also, this is like one of like the. So the ones that the last one we just did are actually newer ones, I guess. Newer activities and stuff. One of the easiest ways to explain how computer systems provide services to other systems is to use an analogy. For example, how shops offer services to their customers. Let's have a look at a piece of takeaway. I got water. I do not have water. It's Friday night and Alice and Bob feel like having pizza. Alice looks at Luigi's pizza menus and tell Bob which pizza she wants. Okay, Bob takes the car, enters Luigi's address into the GPS, and starts driving. Once Bob arrives, he enters Luigi's and places his orders. Give me a large pepperoni pizza and a Coke. The employee acknowledges the order and starts making the pizza once the order is ready. Bob returns home and has a lovely night with Alice. Okay, this seems like a straightforward process, but don't be fooled because we are used to ordering pizza. Hold on. We're used to ordering pizza. We have an internalized process. Let's have a closer look at each step. Okay, so so the client and server. That's why it's called client and server. I don't know if that's why, but like I get it. So the client is Alice. Okay. Okay, request and response. Okay, one less pepperoni coming right up. That's request and response. Protocol, order, rules, and language for communication. Okay, port A, takeout, restaurant delivery. Okay, access point. Then domain name and IP address. Okay. Okay, so in our service client server, in our analogy, Bob and Alice choose to use a pizza takeaway service. Okay, so Alice is the client who passes her order to Bob, who then passes it to the server at Luigi's Pizza. In computer terms, we can translate this as Alice using, for example, a browser to navigate to a website. The browser is the client that requests the web page, and then the server is the system that serves for it. Note that the client is the one who always initiates the request and response. Alice requested a large pepperoni pizza from Luigi's. Be careful, this request was not made to Bob. Bob was the one who brought the request to Luigi's. What is important to realize is that if the request is not formatted correctly, or the request is resources unavailable, we will get an error response. For example, Bob returns to Alice with the message that there were no pepperoni pizzas, or that the server did not understand the order. In computer systems, we can say that Alice used a browser, which is the client, to request a web page from a server, which then sent the web page to the client. So protocol. One of the things we don't often realize until we go on a trip or to a foreign country is our language. When Alice formulates her request to Bob, she used the language Luigi's Pizza to understand. Luigi's Pizza understands. Additionally, Alice uses the menu to determine which orders she can place. Bob understood the request, language, and order, and went to Luigi's to bring it. He received a response he understood and brought it back to Alice. We can compare Bob to a protocol that computer systems use to communicate. A protocol defines how a client can communicate with a server. This definition includes which commands do the client and server understand, the GET command, how a request is structured, first the command and then the order, what syntax is used, which is the language, what response should be given to which type of request, a request for pizza results in receiving the available pizza, what response to give to faulty requests. So like no pepperoni, and that is a typo. I found a typo. No pepperoni pizza available. A port is used to identify a specific service running on a system. When a client wants to access a service on a server, they must connect using the correct port. Imagine that Luigi's takeaway. Imagine that Luigi's takeaway service requires customers to enter through a specific door. Everyone ordering a takeaway uses that same door. In the same way, a service on a server listens on a specific port. Now imagine that Luigi's offers multiple services such as takeaway, dining in, and delivery. Each service uses a different door. Door A for takeaway, door B for the restaurant, and door C for delivery. Similarly, a single server can run multiple services at the same time, with each service identified by a different port. DNS. When Alice sent Bob her request, only the name of the pizza was known. With that alone, it is not possible to reach the destination. So Bob entered Luigi's Pizza into a GPS device, and the device returned the coordinates for Luigi's. DNS stands for Domain Name Service, which we know, and works similarly to a GPS. When you enter the name of, for example, a website, DNS resolves it to a server's location. These location coordinates are called an IP, address in computer terms. Imagine this IP as the address to your home, but for computer systems. Let's look at the next test to see how the client server. Okay, what do we use to identify a specific service on a server? So we know that that's a port. What do we call the address of this address? That's No, that's internet. Yeah, internet protocol. web communication. Oh shoot, we're about to use a machine. Hypertext Transfer Protocol, which is the HTTP, abbreviated as HTTP, is a stateless client-server protocol used for the World Wide Web. This means that each request is processed independently, without the server retaining information about requests. Although the protocol itself is stateless, modern websites and web applications implement mechanisms to introduce statefulness at the application level. For example, when you log onto a website using your credentials, the server creates a session identifier, often stored in a cookie or token, that is sent with each subsequent request. Without these mechanisms, you would need to authenticate again with every new request because the server would have no memory. Yeah, that's like one thing. Like, I always press remember me because I hate putting in, like, when I'm visiting a website, I hate when they do not remember me. So, like, I understand that, definitely. That's why I always say, like, allow cookies if it's, of course, like a very trusted website, of course. So that's what I like. HTTP commands. The main specifications that define HTTP, also called request for comments or RFC documents. There are 9 core commands. In HTTP lingo, we use the term method instead of command. Below, you can see an overview of these methods: get, post, put, delete, patch, head, options, connect, trace. We will focus on discussing one of the 2 most common methods post, which is get. One of them is get, and then we will approach this practically by examining the request a browser sends when you navigate a website. Click on the virtual machine below. This will show a new window in the split screen where we can open a website and inspect the get request. If the split screen is not moving, click the blue start. Okay. Okay, so what did I just press, guys? Ooh, I like that. I like that. That's like kind of cool, like the own like VPN, like virtual private network. Okay, so your machine is initializing. This is pretty cool, guys. This is pretty cool. So what is gonna happen right now? Okay, so this is so cool. This is so cool. Hold on, guys. Give me 1 second, guys. Alright, so we should be good. This will show a new window where we can get a website and inspect. So do we like what do we do here? The get method is actually pretty straightforward. We can use. Oh shoot. Okay, hold on, wait. That's pretty cool. Like, this is so cool. For this example, get we can use this method to retrieve a resource from web server. For example, get HTTP blah blah blah. This request retrieves the Tryhackme'S website's homepage. You don't need to type in this request yourself. When you open a browser and type the link, the browser constructs a message behind the scenes using information you provide and other fields defined in the HTTP specifications. When the web server receives a request, it sends a response that includes the status code and the requested information. This image below shows the flow of the request. So this is the request and response. We did this yesterday. We learned all about that, the 7 types. Let's have a look at an actual GET response and its request and its response. Navigate to the virtual machine that opened next to the screen, then click on the Firefox. Once the browser, the web page, okay. So let's go back to the browser. Okay, we should show. Proceed by pressing F2 or right-clicking the browser window and selecting Inspect. This will open the Firefox Developer Tools, which allows us to inspect. Hold on, let's like fix this real quick. Oh shoot. Yeah, I did not mean to do that, guys. So I did not mean to go full screen. So yeah, we just enter, take off full screen. Okay, there we go. But like, I want to like fix it, dude. Alright, so this will open the Firefox Developer Tools, which allows us to inspect. Click on the Network tab as shown as the image below. Just press on Network. How do we get this out of here? Yeah, move. Now reload the page by clicking the circular highlighter on the image above. Oh shoot. Okay, so you see multiple GET responses appearing in the Developer Tools window under the Network tab. Click on the first entry as shown below. Okay, so wow. Okay, so this is interesting. So right now, this is a whole machine, guys. This is crazy. Like I feel like I'm like a hacker right now, guys. Okay, so in the right-hand panel, we can see more information about our GET requests. We won't go much into detail, but let's have a look at some fields. The scheme tells us which protocol was used, HTTP or HTTPS. Okay, so HTTP. No. Okay, so the host tells us the email of the host. We request resources from. Okay, so the host. Okay, we got that. The file name indicates. Okay. Wait, hold on. Where's? So we can see all of that here. Okay, address displays the IP address. Why? Is he talking about like we can see it here? Okay, I see the IP. Okay, and then this field, that's why the address is 127. We are hosting the website on the same device. That's what the address is. Guys, hold on, because this is actually bothering me, because I can, like, I'm having trouble reading, guys. I'm having trouble reading. Status. This field indicates whether the request we received is 200. Okay. Alright. What is going on? Am I getting hacked right now? Chill. You guys saw that, right? You guys saw that. When a request is sent, we will get a response from, when a request is sent, we will get a response from the service. The response is divided into 2 parts, the response header and then the response body. The response header contains a metadata about the response, while the response body gets the requested content. Okay. So the response body, is there a way I can pull it up? The response body. Oh, so this space, okay. So, and then we can see the request by clicking on the response tab when displaying. Response body. Okay. Image below shows the content in the HTML format. That is tough. What would be the host of the following? So let's. So can we like copy this? So like, why is it not like? So I just put it in. So HTTP. Check that. Okay, so let's copy that. Can we like? Can we go on another web browser, bro? Bro. What do we do after this? We press dang it, bro. I'm already selling, guys. Hold on. Oh, once it's not working, then refresh. But like, is this what they're talking about? Like, bro. Guys, spam slow. Spam slow in the chat. Spam slow. In this room, we have explored devices on the internet can offer services to each other. We focus on the client server, which is similar to ordering pizza. The client initiates a communication, and the server replies. Then we continue with an example of the HTTP protocol, which is used for websites. We saw a practical example of how a client. Okay, so we did all that. We're good. We're good. And my achievement, please. Can I get my achievement, bro? Like, thank you. Thank you. All right, how many points were we at? 993. Let's go. All right, so okay, so let's join this room. We're going through another. Okay. Okay, so in previous rooms, you learn what the components of a computer are and how they communicate with each other. In this room, you'll learn about how companies have optimized the computer components to reduce costs and build flexible, scalable systems that power the modern internet through a concept known as virtualization. Have you ever considered how expensive and inefficient it would be if every piece of software or every website required its own physical server? Virtualization was created to solve exactly this problem. Um, your manager asked for help on improving the hardware utilization of a computer. Hold on, guys. Sorry, guys, my dad was calling. Alright, so learning objectives, understand why managing applications on individual physical servers is inefficient, learn how virtualization addresses hardware utilization and scalability challenges, understand the components of a virtual machine, and then learn how containers have further optimized hardware utilization for applications. Before you start, we recommend that you complete the following rooms. So we did all that. Those are all coming soon. So, alright. So before the concept of virtualization, the rule of thumb in IT was one server, one application. In the early days, digital services were run on physical machines, and um, each machine typically had a single clear purpose, such as hosting a website or storing data. As businesses added more services, they naturally increased the number of physical servers, and the one job per box approach became the standard for building reliable systems. This meant that if a company wanted to run a website, a database, an email service, and an internal app, they would need separate physical servers for each one. The problems were obvious: high cost, low utilization, um, slow deployment, hard to scale. If an okay. In short, companies were paying a lot for hardware that wasn't being fully utilized. Alright, so that's crazy. The need for sharing hardware safely and efficiently. Virtualization introduced a new idea. What if multiple applications could share the same physical server safely? Oh. A virtualization layer called a hypervisor was introduced to act as a referee between virtual machines and allow each virtual computer to behave independently, like a physical computer. The building analogy. Imagine if one single person lives alone in an entire 10-floor building. The person uses only one floor, but maintains the entire building, electricity, cleaning, water, and security. Most of the building stays empty and wasted. It's expensive, inefficient, and unnecessary for his needs. Imagine dividing the building into separate apartments. Each apartment has its own door, walls, kitchen, privacy. Different people can live independently without bothering each other, and they can all share the building's main structure. Virtual. Okay. The building is the physical server. The apartments, the virtual machines. Okay. The tenants, the applications, and the building manager, the hypervisor. Okay. Okay. Mm, I'm guessing that's the. All right, so a hypervisor is the core technology behind virtualization. It's a software that creates and manages virtual machines. It is a special piece of software that divides a physical computer into multiple virtual ones. It gives each virtual machine its own share of CPU, memory, and storage, and keeps everything isolated and safe. It manages the lifecycle of virtual machines: start, stop, pause, clone, delete. And hypervisors have two main types of implementation, each of which is used for specific scenarios, from home labs to large data centers. Type 1. Hypervisors run directly on the physical hardware, making them fast, efficient, and ideal for service and professional environments. Type 2. Hypervisors run within an existing operating system, making them easier to install and ideal for learning system or small setups. Below is a table showing which use case is best suited to each hypervisor type. The use cases can run on both hypervisor types, but it's not the best approach given the main objectives of each. Alright, so use case test malicious files, that's type 2. Production server type 1, database server type 1, software testing 2, Linux 2, data center 2. When using virtualization to test, this was long, guys. To test when using when using virtualization to test malicious files, care should be taken to ensure that the host machine does not become infected by the malware being tested in a guest machine. One approach is to use different operating systems for the guest server or to isolate the guest machine so that okay. Virtual machines, apartments. A virtual machine is a virtual computer created by the hypervisor. Even though it's virtual, it behaves as a real machine. It has its own virtual CPU, RAM, storage, and network, and it can run any operating system. It's completely isolated from other VMs. This means that if one VM breaks, VM, okay, the others continue to work. You can deploy virtual machines on your. Why not click on it if it literally said it right there? You can deploy VMs on your own computer using tools such as Oracle VirtualBox and VMware Workstation. This type of software acts as type 2 and lets you run multiple operating systems such as Windows, Linux, and Mac OS. Since you have learned what a hypervisor and VM are, let's take some examples where you might need them. You need to work on different OS like Kali Linux but you can't buy another system. You install a hypervisor and run Kali Linux VM on it. You want to test whether a file is malicious, so you set up an isolated virtual machine to protect your computer from being infected. Containers. A container is a lightweight, isolated environment that runs a single application and all the necessary components to support it. Instead of bringing a whole separate operating system, a container borrows the core of the existing system by running on the kernel, which is the part of an operating system that communicates with the hardware and manages resources such as memory and running programs. Because containers share this kernel, they start quickly and use fewer resources than full virtual machines. But it also means that they must match the host system's type. For example, you can't run a system's container on a Linux machine. Containers behave like small self-contained spaces because they package the application and its dependencies. They share the host operating system, so they start almost instantly. They remain isolated from each other. Um, So a misbehaving container doesn't affect the others. They can run consistently on any machine, making them perfect for development testing and scalable deployments. The easiest way to deploy containers in a VM is using Docker. Docker is an open source software platform that simplifies the process of building, deploying, and running applications using containerization. The image below illustrates the relationship between Hyper VMs, and containers. There's a hypervisor, virtual machine A, that's the V, and it runs two different containers. What the freak? Okay, type 1. So it was type 2. That's what I freaking said. Suppose the company wants to host them. You should use containers. Alright. This is a site. Let's go. After learning about virtualization, you were hired to be responsible for the virtual environment of AutoGallo, a company that has recently started using virtual machines. In this company, they use an application called Virtualization Manager. This application provides a clear view of the overall status of an entire virtualization environment, providing details of each virtualized instance and the physical host. It also enables you to run actions and manage the VMs you create. Your manager has asked you to investigate an issue within the email service. Essentially, everyone in the company stopped receiving emails today, and no one knows what happened. By clicking view site and let's investigate. Yo, this is tough, bro. This is tough. Hold on, but can we like... Yeah. Yeah. Yes! This is what I've been wanting to do, guys. Well, that's perfect right there. Alright, so in the home screen, you should see 3 main sections. Okay? Summary. Where's summary at? Alright, summary virtual machines provides. Okay. Provides details of each VM and enables you to run actions on them. Host, displays usage and performance details for each physical server. Okay. Go to the VM machine section and look for the VM with the name mail server. So, mail server. Looks like this virtual machine has entered an error state. Let's try rerunning this VM using the blue square button. So let's refresh this. Guys, this is what I live for, guys. Okay, so, after running it again, it appears to be working correctly with no problems. So let's create a virtual machine. As part of each team, you create virtual machines for other teams. After resolving this email server, you create a receive task to create a VM to support the marketing team's website. So let's create a VM to host their marketing website. And their machine sites to locate create VM. Right on the top right, click on it. Okay, so we did marketing VM. 4 CPU cores. That's so tough that you can just like create it like this. I never knew about this. We can just do this. Then create VM. Another routine asks that you have to manage. Do we just like put it running or no? Okay. Okay. Another routine asks you another routine task you have is to manage the health of the physical servers and report status to your manager. Go to the host section at the bottom of the page. Okay. By analyzing, we can identify it has some more capacity. It's almost operating at 100%, and it's come on, guys, let's get that one going. Running for the longest time. That's been running for the longest time. So it's this one. Monitoring. Frick, dude, come on, log in, dude. Dash SYS. What does that mean? That it's using the biggest amount of memory, so it's this one, db dash cluster dash 1, db dash cluster dash 01. Alright, let's say after you. So we have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. We got 8. that is housing most of the VMs. Okay, so this one is because these are the physical machines. Let's go. So, like, can we connect this or not? No, it's not gonna let us. Alright, in this room we learn why virtualization is such a critical foundation in modern IT, both for maximizing hardware efficiency and for safely isolating environments. Key terminology. Let's quickly review some concepts we learned in this room. Virtualization enables a single physical computer to act like multiple separate computers. However, the manager software that makes and runs the virtual computers. Virtual computer is a whole virtual computer inside the real one with its own system. A small isolated box for one app that shares the same system as a host. Container images are pre-packed recipes/templates used to create containers. Network ports, special numbered entry points that apps use to talk over the network. We also call the key benefits of virtualization: cost savings, better resource safe testing for cybersecurity, faster deployment, flexibility, portability, and scalability, and centralized management. For the learning list, with this development, you're ready to explore the cloud concept and the cloud computing fundamentals, which is eventually containerization and automation to provide scalable on-demand. I am ready to cloud. Great work, BC1. Let's go. Oh, yeah. All right. So, is this our last? Yes, this is our last one. So, I'm really excited for this one. Let's join it. Okay, so there's only like 4 tasks, so it should be quick. Wait, we're doing an attack box? No, but we are doing a virtualization. I don't know, virtualization is just such a cool word. Imagine you have a fantastic idea for an app that helps students practice cybersecurity. You host it on your own computer in your country. But what can you do when users from the other parts try to access and experience lag? What if many students connect at the same time or your computer is turned off? These limits make it hard for the app to grow. That's when cloud computing comes to play and solve these problems. The cloud is built on top of technologies you already learned, like virtualization and containers. These enable running many applications efficiently on shared infrastructure and quickly creating or changing environments when needed. In this room, we will explain the basics of cloud computing and how this impacts the way modern applications are built, deployed, and used every day. Alright, so we got this one. Okay. Oh, give me 1 second. No, let's not get distracted. So, cloud computing is the perfect solution for the challenges in the application you've designed, such as moving your files from a single laptop to online storage that you can access anywhere. Instead of running your app on one computer in one country, the cloud lets you use computing sources over the internet. This makes your application easier to access, more reliable, and ready to grow as more students start using it. How servers evolved to cloud. Before we start delving into cloud details, it's helpful to understand that cloud computing did not appear suddenly. It is a result of many years of changes in how servers were used and managed. At each step, businesses look for ways to reduce costs, use resources more efficiently, and make their applications easier to run on scale. The timeline below shows this evolution from physical servers to the clouds we use today. Physical servers, 1960s to early 2000s. Physical companies, servers in company buildings, one server, one job. Expensive, slow to scale. Virtualization, multiple virtual servers on one machine, better. Okay. Alright, automation and remote management. Servers managed over the internet. Early automation infrastructure became used faster and easier. Cloud computing, rent virtual computers and storage on demand. No hardware, ownership, elastic scaling in minutes. Global scale platforms. They focus on apps and not servers. Okay. So, cloud benefits and characteristics. After seeing how applications evolved from physical servers to the cloud, it's becoming clear why cloud computing is so widely used today. The cloud was designed to address common problems, including limited capacity, high cost, and slow growth. The following benefits and characteristics explain how cloud computing makes applications easier to run, scale and manage. Scalability, easily scale up or down as your application needs change. On-demand self-service, create or remove servers and storage instantly without waiting for the hardware. Pay only for what you use. You are charged based on usage, not upfront cost. Security. Providers protect the infrastructure with strong security measures. High availability. Applications keep running even if part of the system fails. Global access. Your application can be accessed by users anywhere in the world. Okay. So in simple terms, the cloud enables IT resources to be flexible, cost effective, and easier to manage. Types of clouds. So this flexibility provided by cloud computing, allows applications to be run in different ways depending on your needs and level of control. Because of this, cloud providers offer multiple models for deploying and using applications suited to different scenarios. Let's start with the deployment types you can choose for a cloud environment. Public cloud, used by startups, web apps, and global apps because it is affordable, easy to scale, and requires no infrastructure management. Public cloud services are preferable for nearly every use case. Private cloud, used by banks, healthcare, and government organizations because it offers greater control of the customization and compliance for sensitive data. Okay, hybrid cloud, used by companies like e-commerce platforms that need to keep sensitive data private while still scaling publicly during high demand. Just like there are different ways to deploy a cloud environment, there are also different ways to use cloud services. Depending on your experiences and needs, you can choose the level of responsibility that fits your application. Let's look at the main cloud service models. Infrastructure as a service. You rent basic computing resources such as virtual server storage and networking. You are responsible for managing the operating system in your application, while the provider manages the physical hardware. Platform as a service. The cloud provider manages the infrastructure in the operating system. You focus on building, deploying, and running your application without worrying about servers. Software as a service. Okay. You use the complete application over the internet. The provider manages everything. You can access the software through browser or app. For example, Gmail or Zoom. Think of cloud service models like different ways of renting a place to live. So, renting an empty apartment, you choose furniture. Okay. Okay. You can move in and not focus only. Okay. Okay, so there are major cloud vendors. There are several cloud vendors offering a variety of services, but Amazon Web Services (AWS) is the industry leader with the most extensive offerings and global reach. Other well-known cloud providers include Microsoft Azure, a strong competitor, especially in enterprise. Okay, so here we have. Okay. Okay, how companies are using the cloud. Netflix runs its entire platform on AWS. I did not know that. So it can scale globally, stay online during peak demand, and stream content reliably to millions of users at once. Spotify uses the cloud to handle millions of songs and users, scaling quickly when new music or features are released. Instagram relies on the cloud to store massive amounts of photos and videos and deliver them fast to users around the world. Online stores use the cloud to handle traffic spikes during Black Friday without buying permanent infrastructure. Okay, so these companies use the cloud because it lets them scale easily, reduce costs, stay reliable, and focusing on improving their products instead of managing hardware. Next, you'll apply these same ideas by deploying your cybersecurity training app in a simulated cloud environment. Um, so unexpected increase. So that just happened. So so what is Okay, so these. Wait, hold on. What is the characteristic of cloud environments that enables you to handle an end scalability? No, high availability. I don't know. Yeah, I think I was right. Scalability. Let's go. What is the most common type? What is the most common type of cloud deployment used? What is the most reliable type of cloud deployment used? Yeah, so public. So they want to deploy an application focusing on only. That's the service. Software as a service. No, infrastructure. Infrastructure. No? Suppose you want to deploy an application to the internet focusing only on application development infrastructure to others. Oh, I was thinking platform. I thought platform was the. Okay. So I was thinking of platform. It's just like I thought it was like the second one. I don't know why I put infrastructure because I think because it said infrastructure. Okay. So here we have in this exercise you use a cloud interface similar to the AWS platform. The goal is to not memorize buttons, but to understand how cloud resources are easily created and managed in a real-world scenario. Basic cloud terminology. EC2 is virtual computer server. It still represents a virtual computer in the cloud, just like a real computer has a CPU and memory. You're adding a computer to your RAM instance type. Instance types describe how powerful the virtual computer is. Hold on. Alright, guys, give me 1 second. Give me 1 second. I have to make a call real quick. Okay, so let's continue on. So instance type is some have more CPU and RAM, and they are therefore more expensive. You choose the instance type based on your needs, knowing that bigger instances, which is more power and a higher cost, minor instances, less power and a lower cost. So deploying your environment, you'll create 3 virtual computers, EC2 instances, to host your server security training application. This aligns with the infrastructure such as the infrastructure as a service model that you previously learned. As cybersecurity practices often require full access to the operating system, this allows you to install tools, configure the system, and safely simulate attacks and defenses, just like in real-world environments. Okay, so first you need to choose a region where your resources will live. Okay, so you can do it at the top right. Okay, we did that. Okay, for example, your reason for geographical and the location. Creating virtual machines. Now go to the create virtual machine. Did I say machine? And instance name. So let's create this virtual. Let's create this. T3. Now let's create 2 testing computers for users to practice their cybersecurity skills. Since these are 2 test machines. Since these are tests, let's use a more powerful insert type, MF MP large. Okay, so because a lot of people are going to be using this, we need it to be a large machine. Did I put that one micro? No, I put it large. Okay, good. Okay, so, I don't see. Okay, your insert should look like this. Application interface. Oh shoot, we didn't even create it. Hold on. Okay, hold on. How do we edit this? Because I think I did the wrong thing, guys. Okay. Okay, there we go. Okay, so let's analyze how much credit is costing. Okay, so 10, 10. Okay, so 170 credits a month. So we're using 170 credits a month. Okay, so currently you're still developing your application, so you just have not accessed your platform. We can optimize costs by stopping the 2 study machines and review the new costs of your environment. Go to the instances block, and click the stop for study machine 1 and 2. Guys, we did this whole thing wrong because we didn't freaking do it. Okay, so it was like 70, right? It was 140. No, shoot, because the only ones we created. 150. What would be the total running cost of the entire environment you created if you added a 3rd study machine? So let's just add like BC1. Oh shoot, what did we do? T3 small, okay. I thought it was gonna like skip, not like submit it. T3 small running. 168. 168. No, because like T3 small is 80. Okay, let's figure it out because we have a lot right now. We have a lot. We have a lot. 188. Let's go. All right. So, in this room, we explore the core ideas behind cloud computing and how it enables flexible, scalable, and cost-effective access to computing resources. Let's quickly review some concepts that we learned in this room. Public cloud services you access over the internet that many people. Okay. Hybrid, a mix, just from one company. So that's open. You rent basic computers like, okay, ready to use. All right. You learn how it was. So did we like pass it? Like, where's my achievement at? Computer fundamentals. Where's like my computer fundamentals? Like, did I get it? Let's try this. This. I bet. So, guys, we only have 3 more. So we're locking in. We're close to the certificate. So let's lock in and yeah, let's just lock in, guys. It's not anything crazy. Kind of like go down. I don't want to go down on that. Okay, so okay, so yeah, we're chilling right now. So thank you guys for watching. Of course, thank you guys so much for watching, and thank you for coming along with me on this journey. I really do appreciate it. I really do appreciate all the love. You know, as I always tell you guys, like the OGs are gonna stay. And see me complete my cybersecurity journey as a professional, a professionalist in the cybersecurity field. So let's go, and I'll see you guys on the next one. So yeah, guys.